So let's look at frequency analysis of EEG. In this lecture, I'm going to cover a few topics. It's going to be a methodological lecture. I'm not so much going to explain, I'm not going to give a lot of examples of where frequency analysis is useful. Mikkel on Monday has already given examples of like the dominant frequencies that we observe in the brain, such as the delta, the theta, the alpha, the beta, and the gamma bands. And I'm assuming, since you're all neuroscientists or you all have a medical background, that you're all familiar with these oscillations that we can observe. So what I'm primarily gonna focus on is the methods, so how we use sines and cosines and how we use Fourier analysis, and factors that influence frequency analysis, such as the frequency resolution, the Nyquist frequency, and the highest frequency that we can estimate. So it's very much on the analysis, but for frequency analysis, we're not necessarily expecting a very precise timing. So what we're now basically assuming is that these arrows don't really exist. So there's just like a very approximate timing, so you know when the participant closed their eyes or opened their eyes, but it's not necessarily indicated with a very precise sequence of triggers. So when would you want to use frequency analysis? So not all brain activity can be captured in the event-related potentials, and spontaneous brain activity shows oscillatory and rhythmic patterns. And EEG frequency analysis makes sense when participants are not doing anything specific, or which is also known as resting state. And resting state can be recorded with the eyes open or with the eyes closed. And if participants close their eyes, then we typically see alpha waves appearing. So that's also what we saw the day before yesterday with the EEG system. When we had the participant close their eyes, we saw very nice alpha waves over the occipital electrodes. We also make use of frequency analysis when participants are doing something which is not specifically timed. So one of these situations that we encounter quite a lot at the Donders, and it's something that I also mentioned before, is that we do a lot of research with children, with infants. And we have these infants, for example, watch movies. And if they watch a movie or if they watch something happening, like slow movements, etc., we don't really know at which moment in time the brain activity happens. So when the continuous stream of stimuli can be split into well-timed individual items, then you can look at the earpiece. So if you, for example, have a very clear stream of words where every word can be coded with a trigger, then earpiece makes sense, or temporal response functions, which is for overlapping earpiece. But when you're interested in changing the oscillatory activity around an event, then also we can use the timing, and we can use a time frequency analysis. So frequency analysis is often used to compare resting state data into two groups, for example, patients and healthy control participants, or to compare two experimental states, for example, before and after treatment. Frequency analysis by itself is not so often used in cognitive experimental paradigm with well-defined stimuli and responses. Because if we have well-defined stimuli and responses, that is something that we use in the analysis by computing ERPs or by doing time frequency analysis. If I'm saying frequency analysis, sometimes I'm saying spectral analysis, sometimes I'm saying Fourier analysis, and they're all the same. They're all based on the same principle, and Fourier analysis is a mathematical approach that takes a complicated wave, which can, for example, be the sound, but it can also be EEG, and it breaks it down into its basic ingredients. And with Fourier analysis, we assume that these basic ingredients are sine waves of different pitches and volumes. So that's if we think about that's if we think about sound. So here you see a few examples of delta, theta, alpha, and beta waves, and they all map onto different peaks in the frequency spectrum. So what we have here along the horizontal axis, is time. So this is really how you see the signals on screen if you're doing the recording. And after the analysis, what you get is, along the horizontal axis, you get different frequencies. So what we're doing is we're trading time for frequencies. And along the vertical axis, we see the relative amplitude of the different peaks. So there's delta activity, there's alpha activity, there's beta activity. And it's these peaks that we then study in relation to the experimental contrast. Spectral analysis or Fourier analysis consists of deconstructing a time domain signal into its components. And the components that we use are simple oscillatory functions. So we have sines and cosines. And one of the concepts that we use here is, so one of the concepts that you have to understand is the frequency. So frequency is expressed in hertz. So if you have a sine wave, and if it goes up and down once per second, it's a 1 hertz signal. When it goes up and down twice per second, it's a 2 hertz signal, etc. Taking it the other way, when it goes up and down once per half a second, it's also a 2 hertz signal. So twice per second is the same as once per half second. It's just like we have a slightly shorter oscillation. And something that you have to keep in mind is that the frequency is 1 divided by the time that it takes to go up and down. Or the frequency is 1 divided by the time that one oscillation takes. So this is something that we also used the day before yesterday when we were looking at the EEG. So the EEG, like I recognized the alpha, and then someone asked, well, how do you know that this is alpha? So what I did is I basically looked at the screen, and there were these vertical stripes indicating 1 second, and I counted the number of times that it went up and down. So I counted approximately 10 bumps in the signal in 1 second, which means that it's a 10 hertz signal. And that's consistent with alpha. And on top of that, I could see that it was on the occipital electrodes. The principle of spectral decomposition is that we have a complicated signal, for example this, and we assume that this is built up, or we model this by multiple individual frequencies. So if we add these 3 frequencies that you see over here, if you add them together, you get something like this. And the more frequencies we add, the more complex the shapes of the time series can become. Each of these frequencies maps onto a peak in a spectrum. Okay, so with EEG, so Fourier analysis is a mathematical technique. What we do with Fourier analysis in EEG, that we always have a limited amount of time, and that's what we call it the discrete Fourier analysis. We sample the data at a specific rate, for example 500 hertz, and we analyze the data in a specific time window. Fourier analysis assumes that even though we observe the signal in a short window, we assume that it's continuous and periodic. So that this implies that we have sines or cosine functions with an integer multiple of oscillations in the window. So if this is the time window that we're considering, then with Fourier analysis, we're assuming that we have either 1 cycle, as I'm showing here, or 2 cycles, or 3 cycles. We cannot have 1.5 cycle, because what we're assuming is that the signal is continuous and infinitely long. So even though we have not observed the data prior to the window that we're analyzing, or after the window that we're analyzing, the assumption of Fourier analysis is that the signal is a sine wave, and the sine waves just happen to be infinitely long. So here you see a 1 hertz, actually I'm not sure whether this is 1 second, but here you see a sine wave with 1 oscillation, here you see a sine wave with 2 oscillations, and you can have an integer number, so you can have like 1, 2, 3, 4, 5, but you cannot have 1.5 or 3.7 oscillations, because that would lead to collisions, discontinuities over here, and then it's not a continuous signal anymore. One way to think about frequency analysis is, for those of you who are more familiar with the mathematics of general linear modeling, which is a technique that is, for example, used in statistics and that is used a lot in fMRI analysis, is that spectral analysis is very similar to a general linear model. In a general linear model, we say that the data, y, is explained by beta times x. X is then a set of orthogonal basis functions, and these basis functions in the case of Fourier analysis are the sines and the cosines. So we have a number of beta parameters to estimate, and each beta parameter is the contribution of one of the basis functions to the data. Since we have phase and frequency, we have to estimate two basis functions per frequency. So we estimate the sine and the cosine coefficient. And we have one beta for the sine and for the cosine at a given frequency, and they map onto the amplitude and the phase. Just thinking about this from the math perspective, if we have n time points, that also means that we can estimate n independent sines and cosine components. Not more, not less. So Fourier analysis is going to give us a fixed amount of basis functions and a fixed amount of regressors that we can estimate. Since each sine and each cosine reflects one frequency bin, we can only estimate n divided by 2 frequencies. So we have n cosine and sine components. So half of them are cosines, the other half are sines. And they basically come in pairs, and that's why we only have n divided by 2 frequencies. And the frequencies, as I already said, they correspond to an integer number of cycles of the basis function in the time window. So if we look at that as just like a long list of basis functions, then here the blue one indicates the cosine, the red one indicates the sine. The blue one indicates the cosine, but now at 2 hertz. The red one is the sine at 2 hertz, etc., etc. So we make a large matrix with regressors. And on basis of this, so this is the matrix with regressors. That's x. And using the inverse of x times the data, we can estimate the beta coefficients. So this is mathematically correct way of computing a discrete Fourier transform, but it's not a very efficient way. So there are faster ways, and those are called the fast Fourier transform. So the fast Fourier transform does this much smarter, but you don't really have to understand how the fast Fourier transform works. What is important is that these sines and cosines, that they're orthogonal. If we now look at one pair, so if we look at one cosine and one sine, then the cosine and the sine can be mapped onto a plane with the cosine along the horizontal axis and the sine along the vertical axis. And both for the cosine and for the sine, we're going to have a certain amount, like a certain beta value. And these two beta values together, they form an arrow. So this arrow has a length, and this arrow has a certain angle. And it's this length and the angle that represent the phase and the amplitude of a certain frequency. So the cosine and sine waves correspond to these basis functions, and the basis functions have an integer number of cycles in the time window that's being analyzed, and these basis functions are orthogonal. So if we have a 1 second time window, then the lowest frequency that we can estimate is with an oscillation of 1 second, so that is 1 hertz. That means that the next frequency that we can estimate is 2 hertz, or 3 hertz and 4 hertz. So the frequencies that we get along the horizontal axis of the frequency spectrum depend on the length of the window that we're analyzing. If we take a window that is twice as long, so if we take a 2 second window, the frequencies that we can estimate become 1 divided by 2, and we can estimate frequencies that are closer to each other. So we can estimate frequencies at 0.5 hertz, because the slowest oscillation that we can fit in is half a hertz. Then the next one is 1 hertz, 1.5 hertz, etc. So that means that in the analysis, we have to think about the frequency resolution that we want to achieve. If we take a very short time window, we're going to have a very poor frequency resolution. But also if we take a very long time window, we're going to have a very high frequency resolution, and possibly a frequency resolution that is higher than what we would need. If we take a 10 second time window, we're going to have a frequency resolution of 1 divided by 10. And that means that we're going to estimate frequencies at 0.1 hertz, 0.2 hertz, 0.3 hertz. And the brain oscillations are not that precise, so that they are very sharp. For a 50 hertz activity due to line noise, this would be a very appropriate technique. And this is what we use when we use a DFT filter. But if we analyze brain activity, we just have to realize, well, alpha is approximately 10 hertz. It's not exactly 10 hertz. So trying to get a very exact estimate of the alpha frequency is not going to work. It's going to be a broad peak anyway. So we have to find a trade-off between the length of the window and the frequency resolution that we want to obtain. When we have a long window, we get a very high frequency resolution, and that might be useful if you listen to the radio, which has very sharp frequencies, but not when you listen to the brain, because the brain has very blurry frequency resolutions. So these physiological oscillations like alpha, around 10 Hertz, they fluctuate a bit, and they differ also from participant to participant. And there's no reason to estimate the spectral content at a higher spectral resolution than those fluctuations. If we now think about how we do this in practice, it means that we take the data, we apply preprocessing, and following the preprocessing of the EEG data, we cut the long recording that we have into short segments of a certain length. Then we estimate the power spectrum for every segment, and then we average those. And the averaging of the power spectrum makes it much more robust and less sensitive to noise. When we looked at earpiece yesterday, then the average of the noise in the earpiece goes towards 0. So if we have noise in a trial, and we know that we always have noise, then after averaging more and more and more, the baseline goes towards 0, because the noise can be both positive and negative. That is not the case with the frequency spectrum. The power that we compute is always positive. The length of the vector is always positive. So that means that if we average over trials, the power is not going to go towards 0. The power is going to reach a certain value, and that's just like the noise level. And that's simply a consequence of us looking at power. Another thing to be aware of is the Nyquist frequency. And the Nyquist frequency relates to the sampling frequency that we use to sample a signal. So what I'm showing here is data that is sampled at fixed points. So let me just start the video once more. So we have fixed points along the horizontal axis, and the continuous line is the real signal that is being sampled. So the continuous line, you should think of that being the EEG. And initially, the EEG is nicely captured, but if you just look at the points over here, then at a certain point, the points start showing weird patterns. And these weird patterns cannot really be distinguished from one another. So the frequency that you see here, and I'm not sure whether I can stop it actually. I was hoping that I could stop it. No, I cannot stop it. But let's just wait a little bit. So when this peak is approximately towards the end, what you see here is in the blue, the real signal that we're capturing. But here in orange, you see the signal that it resembles. So the high frequencies and the low frequencies, if you see this, they cannot be distinguished. So this relates to the Nyquist frequency, and the Nyquist frequency is the highest frequency that can be resolved, and it depends on the time between samples. If the time between samples is too large, given the frequencies that are present in the signal, or the frequencies present in the signal are too large, the time between samples is too small, or the frequencies are too large, then we get aliasing. The sampling frequency that we have is 1 divided by the time between two samples. So if we sample at 500 Hertz, the time between two samples is 2 milliseconds. And the Nyquist frequency is half of that. So that means that the Nyquist frequency is half of the sampling frequency. So with an EEG amplifier that samples at 500 Hertz, the highest frequency that we would be able to estimate is 250 Hertz. Frequencies that are present in the analog signal prior to sampling are still going to be sampled, but they're going to end up as noise at lower frequencies. So that is why it's important that the EEG amplifier is built in such a way that high frequency signals are filtered out prior to the signal being digitized. And EEG hardware often uses an anti-aliasing filter. So in practice, if you look at the power spectrum of an EEG signal, you're not going to see the signal up to half the sampling rate, but often you're going to see it only to like 1/3 or 1/4 of the sampling frequency. So I showed you this unicorn amplifier, the very small one, the 8-channel version. So that one samples at 250 Hertz. So in principle, you would expect that you could record signals up to 250 divided by 2 up to 125 hertz. But in practice, it has a filter built in, and all the higher frequencies above, half times the sampling, a quarter times the sampling frequency, so half the Nyquist frequency, are filtered out. So with the unicorn, we don't really see signals that are above 70 hertz or 67.5. And that is like a limiting factor that you have to be aware of. So if you use the unicorn for ECG recordings, or if you use the unicorn for EMG recordings, you're not going to get a very good representation of the signal, because the ECG has a very sharp peak and the EMG has a lot of high frequency activity. So if you want to record high frequency activity, you need to sample at a high sampling rate. Whereas if you're interested in lower frequencies, then sampling at a lower sampling rate is also fine, as long as you use an anti-aliasing filter. Any questions about this? This is really an important consideration when you're going to get an EEG amplifier, and it's something that you have to keep in mind. Sampling at high frequencies gives you more freedom to see all signals, including the artifact signals. But sampling at high frequencies also results in larger files, so processing is going to take longer, and there's often this trade-off. I must say that at the Donders, by default we sample at 500 Hz. So our amplifiers allow sampling at various sampling rates, but by default we sample at 500 Hz, since that gives us information about the EEG spectrum to about 125 Hz, like 1/4 of the sampling frequency. Sometimes we're interested in gamma band activity, so gamma band activity can be like up to 80 Hz or possibly even up to 100 Hz. So we're able to capture all the EEG activity if we sample at 500 Hz. Whereas if we would sample at 250 Hz, we would not be able to study the gamma band activity. But if you're interested in lower frequencies, then actually sampling at 250 Hz would be fine. Okay, so very practically, so what we have is we have a continuous signal that we, for example, recorded while the participant had their eyes closed. We cut the signal into short snippets, and for each of the snippets we compute a spectrum, and we average those spectra. That gives us the average spectrum. What we do, however, is we try to avoid spectral leakage. And with spectral leakage, we basically push the signal at the edges a little bit towards zero. So that is why it is recommended to segment the data with some overlap. So what I'm doing here is I'm using approximately 40% overlap. So every window has 40% overlap with the previous window, and then again 40% overlap with the previous window. We compute all the spectra and we again average. So why are we using this overlap? So that has to do with spectral leakage. We're assuming that the signal in each segment is continuous, and we're assuming that it's continuous over segment. So we're assuming that over here it's continuous. And we're assuming that it's periodic and that it fits within the window. So a signal that jumps from the end to the start is going to need a lot of frequencies. And the effect of intermediate frequencies appearing at intermediate frequencies appearing at other frequencies is called spectral leakage. And I'm going to show this in the next slide. So tapering or windowing is a method to reduce spectral leakage. So this is the happy case. We have a window of 1 second and we have a 2 Hz oscillation. So we have 2 full cycles. This is a situation where we have a window of 2 seconds, but we have 2.5 cycles. Or here we have 3.5 cycles. So the assumption that we make in Fourier analysis is that the signal is continuous. So if we look, here the signal is nice and continuous. So if we just repeat this window, so we're just going to take a copy of this window, we're going to put it in front. You see that the signal is nice and continuous, and also here. But if we take this window and we're going to put a copy prior to it and after it, what you see happening is that you get these very sharp transitions. Or here, with 3.5 cycles, you even get jumps, so discontinuities. If we do frequency analysis, these jumps have to be explained by high frequencies. So that means that the signal that we have, so in this case the 2.5 Hz signal, it doesn't fit within the integer number of cycles, and it has to be explained by a lot of other frequencies. Tapering is a method that we use to make our spectral analysis more robust for those frequencies which we cannot estimate. So what we do with tapering is we multiply the data in the window with something that pushes it towards the side. So this is what we call a taper or a windowing function. And after computing the multiplication, what you can see is that the data at the edges becomes continuous. So that means that tapering helps to reduce the effect of spectral leakage. So a common taper that we use a lot is a Hanning taper. A Hanning taper is basically looks like a half a cosine. If you don't use tapering, you're just going to get a lot of spectral leakage, and your spectral estimates are going to be worse than what they have to be. And that is because the brain doesn't care about the window that you're using. So if you're analyzing your data in 1 second snippets, well, you could say, well, I'm looking at alpha activity, but perhaps the alpha activity is at 10.5 hertz. And at the 10.5 hertz activity is going to have spectral leakage, which means that you're going to get peaks at frequencies where you don't expect them. Because 10.5 hertz is not a frequency that you can estimate with a 1 second window. Tapering helps to avoid this. Tapering makes the data slightly smoother. So the general recipe for frequency analysis is that we use it if you don't know when in time something is happening, and if you assume that the brain activity is stationary over a longer time window. So what we do is we take a long segment in which the EEG is assumed to be stationary, so we read the data into memory, and then we make one long segment, for example 10 seconds after closing the eyes, so that the participant's brain activity has settled into the eyes closed situation, up to the moment that the experimenter gives the instruction to open the eyes again. So we take that window, which might be 5 or 10 minutes long, and then we segment that into shorter time windows of, let's say, 1 or 2 seconds each. And these windows can be overlapping. We then apply a taper to each of those windows. We compute the fast Fourier transform to get the power spectrum, and we average. It's a pretty simple recipe. So frequency analysis, in a way, is much simpler to do than ERP analysis. And what I've done is I've prepared also a hands-on tutorial to go over this frequency analysis. Do you have any questions about this?